Moving away from indefinite integrals, we're going to look and see what a definite integral gives us when we integrate. So we have a definition here. It says let the function f be non-negative. So that essentially means that all the y values are at either 0 or positive. And so we're going to give a generic little graph right here. And suppose it's continuous on a closed interval a to b. Well, a is typically referred to as our lower bound, and b typically referred to as our upper bound. And you'll also hear these called little a and little b occasionally. So it's defining the area of the region. Now, in area, in geometry, we know we couldn't have negative area, and that's also the case here. But most of our problems are just going to be asking to evaluate the definite integral, which technically is going to be like a net area if it dips below the x-axis. So the area of the region bounded by the graph of f, the x-axis, and the lines a and b, so we'd have vertical lines through here, is going to be this area here. And that's what the definite integral from a to b would compute. When you look at this in terms of geometry, what you're doing is basically taking a bunch of rectangles in here, and you're adding up the areas of all those rectangles. All right, so we've got the definite integral from a to b. And since we're defining this as area, and I didn't mean to put an equals there, let's do this right here. Sorry about that. So the definite integral from a to b of f of x dx is going to equal the total area. But it's only total area if it's all sitting above the x-axis. So this would be a. And so all of this area in here would also be called A. This definition would also have a sister definition, and that's when we were referring to net area. So we can compute what's called the net area anytime that this function is dipping below the x-axis. So in other words, the function f is not non-negative, so it might go to the negative y values. So a situation like that might look like this, where you have a curve coming up. And let's say our A was here and our B was here. So if we were to compute the net area, what that means is it would be taking this area down here, but counting it as a negative number. So we can't really say it's area, but putting that word net in the front kind of saves us a little bit. So when we come over to B, we would then be looking at this as being a positive value. So when you compute with the fundamental theorem, which is what we're going to see in just a moment, the definite integral from a to b, that's going to give you the net area. So we'd count this as negative and this as positive. So net area would equal the same thing, same notation. We just have to make sure we understand that it's net. All right, so we have the fundamental theorem of calculus. Sounds important, huh? Well, yeah, it's fundamental, right? So it's what allows us to be able to take a definite integral and actually get a numerical value for the result. So instead of a family of functions like we were doing with the antiderivatives, we're looking for a single value, a numerical value. And notice too, it also starts out with if f is non-negative and continuous on the closed interval a to b, it's also looking at total area here. Or like I previously mentioned above, it would count all that area that sits below the x-axis as negative if we were dealing with a function f that's not non-negative. But here they're defining as total area. And for the other, it's going to be the same. It's just we have to realize it's net versus total area. So we're going to take capital F, which is the antiderivative. That's what you all practiced in the previous sections. And you're going to plug in the upper bound everywhere you see an x. So these are x bounds right here. X equals a and b. And you're going to subtract out the antiderivative evaluated at little a. This will give us one single numerical value for the definite integral. The difference between definite integrals and indefinite integrals is going to be the bounds that you see here. So that's what makes it definite. And we don't really have to include the plus c, because if you think about it, if we found this antiderivative, it would be capital F of x plus c. But when we plugged in b, so let's say we had this. If we plugged in the upper bound, well, that's going to be over here, and I would have plus c, and then I'd be subtracting it right back out. So I'd have the antiderivative evaluated at a, and then, of course, plus c but the c's just subtract each other out. We're going to take an example that is sitting above the x-axis to be able to compute the total area, because it's a nice little connection to geometry and things that you already know. So we, of course, aren't only going to deal with linear functions like the one in the integrand here, but it just kind of gives us a good place to start. All right, so we've got the antiderivative of 2x dx. So that's going to mean we use the power rule, where we add 1 to the exponent and divide by the new exponent. So that 2 is out front. When we add 1 to the exponent, it becomes a 2. And remember, we divide by the new exponent of 2. Now, instead of plus c, remember we don't need that plus c, because when we do f of b minus f of a, it's just going to add itself in and then subtract itself right back out. So we can change our notation now. So this command means to integrate this elongated s with this dx. Once you integrate, you drop that command. You don't need it anymore. This command right here means that you evaluate. So this is still going to be from x equals a to x equals b, which in this case we've got 0 and 2. All right, so you probably want to simplify anytime you can before you start computing these definite integrals. It'll just save some time with the calculator. And this is equal to x squared from 0 to 2. So I'm going to do my antiderivative, evaluated at the upper bound, so it's always the upper bound, not necessarily the biggest number, minus the antiderivative evaluated at the lower bound, not necessarily the smallest number. So I would take 2 and plug it in, and I would get 2 squared. When I plug in 0, I get 0 squared. So this result is just equal to 4. So this represents the area from this linear function 2x down to the x-axis from x equals 0 to x equals 2. So a graph would look like this if we were to do that. Let's see, so y equals 2x. Y-intercept is 0, and then we would count the slope, which is rise 2, run 1. Alright, so we'd have a nice little linear function going on right here. And what this definite integral is computing is the area from 0 to 2. So 0 to 2 right here. So essentially what we have is the area of a triangle. We could use the geometry formula, as I've noted down here, to find the actual area and see if we actually do get the same thing. So it's not a proof of this fundamental theorem of calculus, but it is evidence, I believe, that would convince you that this is true. So if we had this triangle in geometry, so we'd have a perpendicular here, height, and then it looks like the base is 2, and it looks like the height goes all the way up to 4 when x is equal to 2. So if I wanted the area of that triangle, I would do a 1/2 the base times the height, which is 1/2 the base, which I'm going to call 2, and the height I'm going to call 4. And you can compute this in a lot of different ways, but ultimately you come out with the answer of 4 square units. Now this one would also be square units, but we're not applying it to geometry, so we're going to leave those units off. In number 2, we have a constant function, just y equals 3. So since we just talked about the geometry, let's go ahead and visualize it over here. And so if y is always equal to 3, notice there's no x. You're just going to have a horizontal line. And it can go back to the negative x's if it wants to, but here we're starting from 0 and going up to 2. So this is little a, and this is little b. So let's see, we've got from 0 to 2. So it's bounded by the function, it's bounded by the x-axis, it's bounded by the lower limit a, and the upper limit b. So that gives us what shape? Well, yeah, in geometry, we would call that a rectangle. And you all know that area of a rectangle is length times width, or you can think of it as base times height. So the length of the base down here is 2, and the height we know is 3. So if we wanted the area of this shaded region, we would have 6 square units. So we should get the same result over here, because that's how we're defining this definite integral in terms of area. So when we integrate, in other words, find the antiderivative, we've got a constant of 3. So remember, what function do I take the derivative of to get 3 as the derivative? Well, it'd have to be 3x, because the derivative of 3x is equal to 3. Now, this integral symbol with the dx is a command. It means to integrate, find the antiderivative. But once you've found the antiderivative, we change notation now, because we still have to reference the 0 and 2 somehow, but we don't want to integrate twice. So we change the notation to a vertical bar, where we still have that this is little a, so it's an x value, and we still have this as little b, which is also an x value. So the fundamental theorem says that if I want the area of the shader region, and it will be total area because the function always sits above the x-axis, then I can plug in the upper bound, which is, that looks like a 6, but that's b. So I can plug in the upper bound, which is 2, plugging in the lower bound, which is 0, and I can go ahead and compute these. So 3 times 2 minus, plugging in 0, 3 times 0. 3 times 2 is 6, 3 times 0 is 0, so we end up with 6, just like we did when we used our geometry. And again, you don't have to necessarily put square units, because this one is not referring to area. That's just what we use to define it as. So number 3, you might look at that one as having an inner function raised to the power, but because the inner function's derivative is only 1, so derivative of x is 1, derivative of the constant 0, then we really don't have to involve the chain rule right here, or the general power rule, or formal use substitution. We're going to see that change in a minute, but for this one we're just going to keep as term by term. So we're going to think of, this is our first term and this is our second term. We're going to go ahead and integrate term by term. So when I integrate x, I'm going to have adding 1 to the exponent, dividing x squared over 2. And then for the minus 2 constant, I'm going to have minus 2x. So remember, the command with the integral and the dx means to find the antiderivative, which we've done. Technically there's a plus c right there, but when we plug in the upper bound of 4 and subtract out plugging in the lower bound of -1, those constants are just going to go away. So we have different notation. This means to evaluate this function from -1 to 4. So what we would have is capital F of 4, so not necessarily the biggest number, but it has to be the one in the upper spot, and then minus f of -1. So when we plug in 4, we have 4 squared over 2 minus 2 times 4. And when we plug in -1, we'll have -1 squared over 2 minus 2 times -1. So you can use a calculator for this entire calculation. You just have to be really careful with parentheses over here, especially with that negative being squared, and then subtracting out this whole thing. But you can also simplify a little bit if you like. You've got 4 squared over 2, so that's going to be what, 16 over 2? And we can go ahead and multiply 2 times 4. And when I square a negative, I'm going to get a positive, so that's 1/2, and the negative gets distributed. So that's going to be a -1/2 when I distribute. And over here, -2 times -1 is positive 2. But if you're thinking about subtracting that out, then you're going to have to minus 2. So over here, we have 16 over 2. And then we subtract out the 8. And then we have -1/2. And then minus 2. So the 8's are going to cancel when we evaluate this. And we'll just have -1/2 take away 2. So in your calculator, be sure you have parentheses around the fraction, just like that, and then take away 2, and that should give you like -2.5. So -1/2 and -2 is going to give me -2.5, or -5 over 2. So in number 4, we have the definite integral from 1 to 4, and it's the 2 over the square root of x dx. So we will write this as 2x to the -1/2, and we've not integrated yet, so let's keep that command here. And then we can go ahead and just add 1 and divide. So if we take the exponent of -1/2 and add 1, we're going to get positive, let's see, if we add 1 to -1/2, we're going to get positive 1/2, and dividing by the new exponent and going from 1 to 4. So we can simplify a little bit here. This is 2 times 2 over 1, since 2 divided by 1/2 is like multiplying by the reciprocal. So we'd have 4 and then x to the 1/2 from 1 to 4. So we change from the integration command over to the evaluate command. So this x to 1/2 really is just the square root of x. So that might help you to think of it in terms of that. But you're just plugging in the upper bound of 4 minus the lower bound of 1 and getting a numerical value. So we know the square root of 4 here is 2, and 2 times 4 is equal to 8. Over here, plugging in a 1, square root of 1 is 1, and then times 4 is 4. So we get an answer of 4. If we get a little sketch of what this graph looks like, we're going from 1 to 4. So if we plug in a 1, 2 over the square root of 1 is just going to be 2. And if we plug in, let's see, we need a perfect square right there. So if we take the square root of 4, which is what we have here, x equals 4. The square root of 4 is 2, and 2 over 2 is equal to 1. Now this particular function is not linear, okay, so it's going to do something like this. But if we're only wanting to go from 1 to 4, that doesn't matter so much, because we know we just need to find the definite interval. So this value of 4 is equal to the area between the function. I'm going to use BTW for between. So between the function, the x-axis, and x equals a, and x equals b. So this would be our 1 of a and our b of 4.